Hello, my name is Stefan Rahmstorf and I would like to give you an introduction to some of the most important data that everybody should know about the climate crisis. We live on a planet that is drifting through space, and the climate of our planet is ruled by a planetary energy balance. That energy budget is seen here, and the energy that drives the climate system, of course, is coming from the sun. Part of that solar energy is reflected straight away by the bright surfaces, and the rest is absorbed by the atmosphere and the Earth's surface. Now, if we only had this incoming radiation, we would overheat extremely quickly. Just think about how quickly temperatures rise when the sun comes up in the morning. But the Earth, like any physical body, is constantly radiating energy, in this case, out to space. That is the long-wave radiation, and part of that is captured by the atmosphere on the way out because of gases contained in the atmosphere, which absorb in the long-wave radiation band, and this energy is radiated also back to the Earth. Note that at the Earth's surface we have about 340 watts per square meter of back radiation arriving in this way through the greenhouse effect, compared to only 163 watts per square meter absorbed solar radiation at the Earth's surface. So this back radiation that makes up the greenhouse effect is by no means a small effect. It is simply a major component of the Earth's energy balance. The fact that we can affect climate is not very new. Already the famous German explorer Alexander von Humboldt wrote this in the year 1843. He said that humans are changing the climate by cutting down forests and by releasing large amounts of steam and gas at the centers of industry. Now, the temperature on our planet is indeed increasing in line, as expected, with the increasing greenhouse effect from the increasing load of greenhouse gases in the atmosphere. This is one way to depict the global mean temperature, either in colored stripes that represent 1 year each, starting in 1880 here up to 2019, or as a traditional curve. And you can see that we have witnessed a warming so far of about 1.2 degrees centigrade since the late 19th century. The cause of this warming is also very clear simply by analyzing this radiation balance and the changes to it. This is what we call radiator forcing, and this diagram from the United States National Climate Assessment from 2017 shows that the effect caused by humans, mainly due to the rise in greenhouse gases, by far outweighs any natural climate changes, either caused by the sun or by volcanic activity. And in fact, these are even taken together probably very slightly negative, so that the natural changes would have counteracted a tiny part of the global warming that we have caused. We can also compare the modern warming with the history of global temperature since the last ice age. That is the fruit of decades of paleoclimate research with ice cores, sediment cores, and other sources of paleoclimatic data. And they show that from the Ice Age into the Holocene, the global temperature increased by about 4 degrees Celsius. After that, it very slowly decreased over the past 5,000 years or so. These gradual changes to Earth climate, natural changes, are caused by changes in the Earth orbit, the famous Milankovitch cycles discovered by Milutin Milankovitch in the 1930s. And what you see here is basically driven by the shortest of these cycles, the precession cycle, which has a period of 23,000 years. Now, this natural cooling would very likely have continued had we not bent around this curve dramatically with the beginning of industrializations. We have undone more than 5,000 years of cooling within 100 years, and very likely the global mean temperature is now actually higher than any time in the Holocene, that is, at any time in the history of human civilization. If we look more locally at the German temperatures, we see that the annual temperatures in Germany have warmed by about 2 degrees, so that is more than the global average, entirely expected because the continents warm faster than the oceans, and the global average temperature is a true global average, including also the surface of the oceans that make up 2/3 of our planet. And because the oceans warm more slowly, because of the thermal inertia and the evaporation effects, the land temperatures typically warm much faster than the global average. And that is also the case in Germany. Now, what is this global warming, what effects does it have on human society other than just everything getting gradually warmer? Now, one of the things we notice first is the change in extreme events, and it's a no-brainer that if climate generally warms, you get more heat extremes. And in fact, we have done the worldwide analysis, we now get about 5 times as many records in the monthly mean temperatures, records like the hottest August on record, for example. We get 5 times more of these monthly heat records compared to a stable, a stationary climate. One example is a European heat wave of 2003, shown here, which caused about 70,000 fatalities across Europe. So heat waves are silent killers. Another effect of a warming climate is stronger extreme rainfall events and more frequent extreme rainfall events. There is again simple physics behind this, because a warmer air can hold more moisture, 7% more per degree of warming. And in a case of an extreme rainfall event, this is coming from a saturated air mass that would have 7% more water in it than in a climate that's 1 degree cooler, with everything else remaining the same. And this is why extreme rainfall increases. Unfortunately, also the frequency and intensity of droughts increases in some areas of the globe, especially in those that are already relatively dry. Prime example, Australia, which witnessed this extreme wildfire disaster during the turn of 2019 to 2020, which followed on the warmest and driest year in Australian history, and the Australian Fire Danger Index reached a record value in December 2019, which had never been recorded before. Another physically logical consequence of global warming is a rise in sea levels, and we observe that during natural climate change as well. For example, at the end of the last ice age, global sea levels rose by 120 meters. So remember that, imagine that, 120 meters. We still have enough ice left on Earth to raise global sea levels by another 65 meters. So about 2/3 of the ice that was present during the last ice age has melted during those 4 degrees of warming at the end of the last ice age. 1/3 we have left, and that means, 65 meters. We can't even afford to lose a few percent of that ice mass that is still mainly on Antarctica and Greenland. Now, this data curve here shows the global sea level observed since the year 1700s, the last few hundred years. So far, we have seen a bit more than 20 centimeters of global sea level rise. For the future, we expect this to accelerate, because obviously in a warmer climate, ice melts faster. So the warmer it gets, the more the sea level rise accelerates. Or, if all goes well, the blue curve, that represents the Paris Climate Agreement. That's happening in a climate where temperatures have been stabilized below the 2-degree level. What we can achieve by that is prevent a further speed up of sea level rise. Sea level will then continue to rise, however, for many centuries, because at a steady rate, because the ice simply takes a very, very long time to melt, thankfully. Now, this has all been known for a very long time, and the nations have negotiated for decades, ever since the Rio Climate Summit in 1992, about an agreement to stop climate change and to prevent a dangerous interference in the climate system. And in Paris 2015, finally, this agreement was reached, which stipulated to hold the global temperature to well below 2 degrees above the pre-industrial temperature level, and to make efforts to limit the warming even to 1.5 degrees. Now, the well below is sometimes forgotten when people talk about the 2-degree limit, and also the ambition to limit to 1.5 degrees is sometimes not mentioned, but without that, many nations would not have signed up to the Paris Climate Agreement, namely the vulnerable, the poor nations that have the most to lose from global warming. But what does this actually mean? So how fast would we need to limit, to reduce the emissions? Well, let me first say we have to reduce emissions to zero if we want a stable climate, because of the very long lifetime of carbon dioxide in the atmosphere. As soon as we're still emitting something, we will add to the CO2 pool in the atmosphere like you add water to a bathtub. So only net zero emissions will bring us back to a stable climate. They won't bring us back to the cooler climate we had in 100 years ago or so, but they will prevent further warming. Now, how quickly do we need to reduce emissions? The IPCC report on the 1.5 or 2 degree global warming found that we need to cut global emissions by half by the year 2030. So we have only by now less than 10 years time to cut emissions in half. That is a very ambitious it requires a rapid transition of our energy system, and it is a very ambitious task, but all the nations that signed up to this knew this, and they knew, however, anyone who has looked into this more deeply, how very threatening the climate crisis is, and that's why even nations like Saudi Arabia or Russia that live off selling fossil fuels have signed up to the Paris Agreement. Now, I already mentioned that because of the very long lifetime of CO2, it all just accumulates, and that means we have a limited budget of CO2 that we can still emit in order to limit warming to either 1.5 degrees with 50% chance, as in the green line here, or to well below 2 degrees, let's say 1.75 degrees, with 67% probability. That are kind of two interpretations of the Paris Agreement. It's broken down here to European Union emissions on the basis that the remaining global budget, that is shown here, 720 gigatons for the well below 2 degrees or 500 gigatons for at least 50% chance to stay below 1.5 degrees. This global budget is here distributed at the time of the Paris Agreement at the beginning of 2016 to all nations on Earth based on equal per capita allocation. That is a principle of climate justice, of course. You can debate what is the most fair distribution of this emissions budget, but this is one example how this would work out for the European Union. And you see that with a 1.5 degree target compatibility, we would have to be at zero emissions in the EU by the year 2040, and the more kind of a lenient Paris Agreement target would still require us to be at zero emissions before the middle of the century. If you want to read more about this, feel very welcome to follow me on social media, or in English language I have available this book, The Climate Crisis, from Cambridge University Press, written with my colleague David Archer from Chicago University. Thank you very much for listening.